Welcome to The Explainer. Today, we're exploring one of the absolute most fascinating topics in modern engineering, the incredibly complex physics of flight. More specifically, we're looking at exactly how we engineer that flight before a plane ever even leaves the ground. I mean, it's pretty magical when you stop and think about it, right? We take thousands of pounds of shaped metal and somehow make it soar smoothly through the sky. But how do we actually guarantee that those shapes are going to generate lift? Well, that is exactly what we're going to unpack today.
Okay, let's dive into this. For decades, if you wanted to know how air moved over a wing, you had a really expensive problem. You had to build a physical prototype, rent out a massive multi-million-dollar physical wind tunnel, and run these incredibly time-consuming tests. And if the design failed, well, you had to start all over again. The time and resources required were just astronomical. But today, we have a way to completely bypass that physical hurdle, right from our computer screens.
Here's our mental roadmap for the explainer today. We're going to zoom in from macro physics to micro software steps, and then zoom all the way back out again. So we'll cover 1. The basics of aerodynamics. 2. Enter computational fluid dynamics. 3. Setting up the simulation. 4. Visualizing the invisible. And finally, 5. Real-world aerospace impact.
Starting off with Section 1, the basics of aerodynamics. Let's look at the fundamental forces that allow an aircraft to actually ascend and maintain flight.
So at the very heart of aircraft design is optimizing lift and drag, and that all comes down to Bernoulli's principle. The cross-section of an airfoil is precisely engineered to manipulate pressure differentials. Basically, it lowers the air pressure on the upper surface to generate that crucial upward lift, but we also have to manage the angle of attack. Pushing that angle higher increases lift, sure, but if you cross a critical threshold, the airflow separates from the wing, resulting in a sudden and very dangerous stall.
And this brilliantly illustrates the two primary flow states we deal with in this analysis. On one hand, you have laminar flow. This is where air travels in nice, smooth, parallel layers over the wing surface with very minimal disruption. On the other hand, you have turbulent flow, which is characterized by chaotic property changes and eddies that induce a massive amount of drag. Understanding and precisely managing the transition between these two states is literally an essential metric for any aerospace engineer.
Moving right along to Section 2, enter computational fluid dynamics. Here's our revolutionary, cost-effective solution to that massive wind tunnel problem.
Think of CFD, or Computational Fluid Dynamics, as the modern aerospace engineer's superpower. It's a specialized branch of fluid mechanics that relies on complex numerical analysis and algorithms to solve fluid flow problems. Instead of building a physical model and blasting it with actual air, we use heavy computing power to mathematically predict airflow patterns, pressure distribution, and aerodynamic forces. It is incredibly powerful because it allows for rapid prototyping and endless design iterations without ever leaving your desk.
And one of the absolutely best tools for doing this is SOLIDWORKS Flow Simulation. The real beauty of this software is that it integrates seamlessly right into the CAD environment. So you design your 3D wing, and in the exact same software window, you can test it. It handles both internal flow analysis, say air moving inside a computer enclosure, and vitally for our explainer today, external flow analysis, which is how we actually study the behavior of air moving over an aircraft's outer surfaces.
Let's jump into Section 3, setting up the simulation. Imagine for a second that you are the student engineer tasked with doing this exact analysis. We start with these critical initial steps. First, you'll need to create or import your 3D airfoil geometry right into SOLIDWORKS. Second, you have to define your computational domain. You can think of this as a virtual 3D box built around your wing where the actual simulation takes place. Now, this domain has to be large enough to capture all the relevant flow phenomena so the boundary walls don't artificially interfere with the results. Third, you apply boundary conditions to accurately model your far-field, real-world flight scenario.
Now, what's really interesting about this slide is the crucial fifth step, generating the mesh. Think of meshing kind of like throwing a giant 3D digital net over your wing and the surrounding space. It divides the entire domain into tiny, manageable, finite elements that the computer can then individually calculate. You'll also need to select your fluid, which in this case is air, obviously, and finally, set your inlet velocity to match specific flight speeds and define your turbulence parameters using models like the K-epsilon model.
But beware, because setting this up incorrectly is a total recipe for disaster. Misapplying boundary conditions or assuming unrealistic airspeeds will completely skew your data. But the absolute biggest offenders? Poor mesh quality and choosing the wrong turbulence model. If your mesh is too coarse, you lose all that crucial aerodynamic detail and your accuracy just plummets. And if you ignore whether your mathematical solver has actually reached convergence, your results are essentially useless. So it's a very delicate balance between careful, precise setup and computing feasibility.
Which brings us to Section 4, Visualizing the Invisible. This is where we get to see all those solver calculations finally come to life. Once the software has finished crunching those millions of numbers, it generates some truly stunning visualizations. We actually get to see the unseen. We get velocity contour plots that use bright colors to show exactly where the airspeed is high and where it's low around our geometry. We get pressure distribution maps, highlighting the vital pressure differences driving Bernoulli's principle. We can generate streamline visualizations that draw the actual physical paths of the air flowing over the wing. And crucially, we can visually identify flow separation regions, those incredibly dangerous spots where the airflow detaches from the wing surface, leading to that loss of lift we talked about earlier.
But, it's not just about pretty visual maps. To truly optimize a wing design, we need hard, quantitative numbers. And the CFD simulation outputs highly accurate lift and drag coefficients. By interpreting these precise measures, engineers can make tiny, informed geometric tweaks to improve the aerodynamic efficiency, actively reduce drag, and dramatically enhance the overall performance of the aircraft.
Finally, Section 5, Real-World Aerospace Impact. Let's zoom back out to the macro level to see how these principles are applied globally.
These tools are quite literally the backbone of modern aerospace. Giants like Boeing and Airbus rely almost entirely on CFD to design commercial aircraft that are aerodynamically optimized to save millions of gallons of fuel. It's used to ensure the extreme high-speed stability of military fighter jets. It's used to optimize unmanned aerial vehicles, maximizing drone battery range and maneuverability. Even NASA utilizes CFD to study the wildly complex aerodynamic characteristics of spacecraft as they pass through intense, high-speed phases of flight.
So the crucial point is this: CFD is incredibly powerful, but it comes with distinct trade-offs. On the plus side, it's highly cost-effective, vastly faster than physical testing, provides incredible visual clarity, and allows for rapid design changes. However, look at the limitations. It demands massive computational power, it requires real patience for mathematical convergence, and ultimately, it relies on numerical approximations that are highly dependent on the quality of your initial mesh.
Embracing this kind of simulation-based learning fosters incredible innovation, and it really prepares you for the absolute cutting edge of engineering careers. CFD literally gives you the power to see the unseen and shape the very future of flight. So I'll leave you with this provocative thought. As this incredible simulation technology continues to evolve and become even more powerful, what groundbreaking aerodynamic designs will you create next? Thank you so much for joining me in this explainer. Keep experimenting and absolutely keep pushing those boundaries.